Hey everyone, hope you're doing well. I've got a video on the ambiguous case of sine, and this is usually the hardest area of trigonometry for grade 11 students, so I thought it would be a good idea to give a quick overview on the theory and also how to solve the ambiguous case. Now, if you want to jump right ahead to how to solve a question involving the ambiguous case of sine, feel free to skip ahead in this video. I am going to start with a little bit of theory just to give more context as to why the ambiguous case exists. But if you want to skip ahead, no problem. So for triangle ABC, where I know the angle A, and that would be this angle right here, and the side lengths A and B, I can actually figure out what kind of triangle I'm able to make just from this information. So I want you to take a look at this first triangle here. And this is actually one of the special cases of a special triangle where we would use this triangle to represent some core ratios of sine, cos, and tan. You may recognize it. But the most important thing to think here is that if I were to take the sine ratio of this angle here of 30 degrees, I would need the opposite side, which is 1, over the hypotenuse. And this is correct. If you were to put sine 30 degrees into your calculator, you would see that it equals 0.5 or 1 over 2. And what I can do with this equation here is I can rearrange it just to isolate for this side length. And this side length in our example would be side length A. So I'm just going to move the 2 over here. And I would get 2 sine 30 equals 1. And we could write this equation like so. I could say the magnitude of B times sine A, which is the angle of A, equals the magnitude of A. And all this means is this side length right here equals the hypotenuse multiplied by sine 30. And I'm just getting that from the basic sine ratio. So what I can say is, if this equation holds true in the side length and angle that I've been given, then I have a right angle triangle. So, okay, that's a very specific scenario where side length A equals B times sine of the angle A. But what if the side length A is quite a bit shorter compared to the ratio? And what I mean by that is, if I look at the second triangle down here, if I were to try and set up the sine ratio for this angle, and solve for what this side length should be, it would look like opposite over hypotenuse. And if I isolated for my opposite length, it would look like 5 sine 30. And 5 sine 30 would give me 2.5. But if you notice, in this scenario, my A side length is a 2. So since the side length A is smaller than that ratio we worked on before, the triangle is impossible. Right? Because if I wanted to make a triangle where I have the A angle of 30 degrees, I can't have the A side length be 2, because it has to be 2.5. Otherwise, I can't technically close off this triangle completely and form this angle down here. Now let's look at our third and final example, which will be the ambiguous case of sine. Now, just from the drawing, we can obviously tell that this is not going to be a right angle triangle. But if we wanted to prove that that wouldn't be the case, we can just show that obviously sine 30 degrees should give us a value of 0.5. And if I were to set up the sine ratio here, it would have to be opposite, which is 7, over hypotenuse, which is 10. And clearly, 7 over 10 is larger than 0.5, so this equation does not work. And this leads us to our third description, where if the side length A is greater than B sine A, there are two possible triangles. So, okay, we've shown that it's not a right angle triangle, but why does this scenario say that we have two possible triangles? That has to do with the cast rule. And if I were to write out a quick Cartesian plane here, I'll remind you that the cast rule just tells us when sine, cos, or tan is going to be positive or negative depending on the angle that we're dealing with. So if I look at this example right here, where side length A is 7 centimeters, side length B is 10 centimeters, and angle A is 30 degrees, there are two ways I could actually set up this question. I could set up the triangle where the side length A is kind of sticking out to the right, or I could have it much closer to this first spot here of angle A and kind of create a sharper angle. And if I think about this 30 degrees, if I were to draw that on this plane here, I know that sine 30 degrees equals 0.5. But the interesting thing about sine is that it will be positive in both quadrant 1, because the A stands for all ratios, and quadrant 2, because the S stands for sine. And what that means is there is an equivalent angle in quadrant 2 for sine that will give me 0.5. And the way I'm going to find that is I'm just going to subtract my original angle from 180 degrees. So in this case, it should be 150. And sure enough, if you plug in sine 150 into your calculator, you should get 0.5. So how does that relate to the triangle? Well, if we were to solve for this angle right here, it's going to have an equivalent angle that could be drawn over here. And I can show that with sine law. Because if I were to set up sine law for this first triangle right here, I could say 7 sine 30 degrees equals 10 sine theta. And sine law is just saying that the side length over its corresponding angle equals any other side length with its corresponding angle. Now that's fine, but this theta right here, this angle, could be either the angle in quadrant 1 or the angle in quadrant 2, because it's going to give me the exact same value. And that's why the ambiguous case exists. And let's actually solve for this angle right now. 7 sine 30, or 7 divided by sine 30, will give me 14. And then in order to isolate for the angle, I'm going to have to rearrange things like so. And I'm running out of space, but bear with me. I'm going to need to get rid of this 14 on the left side, so I would divide both sides by 14. And then finally, I just need to inverse sine both sides to solve for my angle. And you'll find that your angle should be roughly 45.6 degrees. We have to remember, though, that this is only the answer in quadrant 1. So when you plug this into your calculator, you're going to get the answer for quadrant 1. We need to figure out the angle that would give us the same value in quadrant 2. So I'm just going to do the usual subtraction from 180, and that gives me 134.4 degrees. So in this first example, I'm going to have an angle of 45.6 degrees. In this triangle, it will be 134.4. And that is what I have drawn right here, where I have the first angle here and the second angle here. Now, usually in an ambiguous case question, they're going to ask you to solve for both triangles because the values will vary depending on the situation. To solve for this angle right here, I could probably just work with 180 degrees, because if I subtract my two other angles, I will for sure get the missing angle. And that should be 104.4. And then to solve for side length C, it's pretty basic. We're just going to follow sine law. You could also use cosine law, but I find it's just a bit more tedious, and whenever I have the choice, I tend to go with sine law. So to isolate for C, I just need to move this over here as multiplication. So if I were to plug all of that into my calculator, I get roughly 13.6 centimeters. And I guess I should clarify that this is centimeters up here. So that's triangle number 1 solved. Now we have to do the same thing for our second case. And this should give me 15.6 degrees up here. And finally, just use sine law to solve for the final side length. Just got to move this all the way over here and multiply. And that gives me roughly 3.8 centimeters. So actually solving for the remaining information in both triangles is going to be fairly standard when it comes to trigonometry. You're just going to be using sine or cosine law. But the trick is to just make sure that when you solve for an angle in your calculator, which in this case would be 45.6 degrees, you have to remember about the second possible answer that exists in quadrant 2. Hopefully you found this helpful. Thank you very much for watching. If you'd like some more help on other grade 11 topics, feel free to click on either of the videos shown in front of you, and happy studying.